That's okay.
Okay,
We
there we
can
go.
begin.
Okay. Um, well, first, ha it's good to see all of you. Um, we we've got we've covered a lot of territory up to this point, and
Steve, can you turn your mic on a little? You're very soft compared to Francois.
I think I am generally actually. Um, how's this?
Little better.
Um, okay, I'll try moving closer to the screen. How's this?
Fine.
Okay.
It sounds good for me. Thank you, Steve.
Thank you.
Oh, well, okay. So then to begin again, thanks. I in talking
We have a
with
good tablet.
okay, let's make sure that I have the right screen showing. And so here, how is that?
Oh, that's perfect. Thank you.
Okay, so the um the topic that we were talking about is how to understand not just stellar evolution in general, but what are the sorts of things that really govern the advanced stages of evolution, and why are they so different than what you have when you're sitting on the main sequence for most of the lifetime of the star. So the idea today is to do everything from kind of late middle age to retirement and then some of the death benefits. The the idea is also, of course, to link with the spectroscopy and things that you can actually observe, including the photometry. So some of this will be perhaps a bit redundant in things we've talked about in the past, but in contrast with most of the objects we've been talking about, like novae, supernovae, mergers, accreting systems, these are more generic, take place over a longer period of time, and involve a lot more physical processes than any of the single ones that we were talking about. But at at the same time, also show up in producing many of the systems that we've talked about. So a kind of background theme is also going to be not just where the elements in the higher part of the periodic table are produced, but something much more basic. The systems we've been talking about, like novae and cataclysmic variables and symbiotic systems, involve extremely compact objects, not neutron stars, but white dwarfs. And one of the long-standing problems in the history of stellar evolution is, where do those come from? Such amazingly abundant normal objects that are just degenerate little buggers that happen to have surface temperatures when they're discovered of order a few tens of thousands of Kelvin and then just die off. Where do they come from? How do they form? And what are the processes that lead to the end states that are far less catastrophic than the ones we've so far covered? That's a long-winded way of beginning things, but let's let's go to a different screen, and we'll start with here. So I can finally use the pad again, and please let me emphasize that if there are things that I'm saying that at any point are not making sense or that you'd like expanded, please, as always, break in, okay? So, to give a start here, excuse me, there's one thing I need to do, which is to turn the video off. Okay, so just to begin with a very basic idea that you all know I mean, we've used this a gazillion times. In the HR diagram, when you build a star, when you finally reach the stage in evolution of a hydrostatic core, and the temperature gets sufficiently high, and the density is sufficiently high that you can get nuclear reactions beginning in the core of the star, what happens is something that passes over an extended period of time. That is, you don't just ignite the core of a star. It builds up to a temperature, and then over the course of a few thousand years, perhaps, the core becomes sufficiently uniformly hot that it begins nuclear reactions by charged particles, by which I mean that if you've got stars on the upper main sequence, then the typical reaction is a proton capture on carbon that goes to nitrogen 13 as the initiating reaction. And we'll call that what it is, CNO. So just the diagram that we'll constantly be using from now on. And on the lower main sequence, it's not sufficiently hot. That is, the protons don't have sufficient kinetic energy to penetrate the carbon barrier because it's a repulsive charge. So when the nuclei are stripped off, the stars that are in this lower portion, that is, the ones that come into pressure balance, mechanical equilibrium at smaller radii and lower temperature in their cores, because the temperature in the core depends on how compact the object is, but also how much mass it has, because that's what determines the internal pressure. The proton capture on carbon being impossible and there being no way to have, say, helium, which is a Big Bang product, producing anything. Okay? You cannot have this reaction. Helium cannot capture a proton and be stable. So the next reaction that's available is for two protons to merge. This is a weak interaction, and the result is you get the emission of a neutrino, and this goes to deuterium, which can then immediately be consumed and go to helium-3, which can then go to helium-4 plus 2p. Okay? The point is this reaction. This is extremely slow, and this is, by contrast, extremely fast. This has a very high temperature dependence because it has to penetrate a repulsive interaction. It has to penetrate what's called the repulsive Coulomb barrier. In other words, you got to slam two positive charges together. And the only way you can get that to happen is if you have a very high temperature. But because there's a threshold for this, that high temperature also has to be at high density. And because of that, and because it has a high dependence on the temperature, it also is a very fast reaction compared with this. Put differently, the temperature dependence here goes something like to the temperature to the 15 where this goes like the temperature to the fourth. It's just a way of characterizing it. So, in other words, here in the proton-proton cycle, you have lower luminosity, and because it is weakly density dependent, both of these go like m squared, but the temperatures are lower, the luminosity is lower, but it's more concentrated in this reaction than in this one. In other words, if you looked at the star, what you would have, if we say, we'll call this the core, okay? And say, where is the actual nuclear reaction going on? The very strong temperature dependence of CNO means that the actual burning itself, the fire, is really very concentrated. But because it's releasing so much energy, the outer part of the region of the core has to convect. Now, I'll come back to that in a little while because this is going to be a central theme also from last time when we were talking about pulsation, that there are three modes for getting energy out of a star. The two that are really important are radiative and some kind of fluid motion like a boiling. And in this case, the CNO, because it's releasing energy so point-like in the core, generates a region around it which is essentially boiling. That is, the core mixes so that although the burning itself is centrally concentrated, the whole core is completely mixed out to some outer boundary, which means that in this you have hydrogen being converted into helium almost uniformly. So that if we look at the fraction, call it the mass fraction, the helium will look like this at the end of the core burning stage, where in a lower mass star, it looks more like this. The reason for that is this reaction is less temperature sensitive. So it's burning not in a center and generating this massive convection because it's got so much energy that it can't just radiate it away. It actually heats the medium up to the point where it's buoyant. In the proton-proton, it's much gentler. So there's burning right at the center, but there's a little less burning a little farther away and a little less farther away. In other words, this can be radiative, not convective. So the inner structure of the star is essentially different. That is, stars in the upper main sequence are uniformly mixed convective cores. And in the lower part of the main sequence, they're smoothly varying profiles. I hope this is clear because this determines everything about the subsequent evolution of this object. It is
Steve, clarification, please. The two little graphs that you drew, the horizontal axis is radial position and the vertical is mass
vertical
fraction.
is abundance.
Okay, got it.
Okay, so we'll call this 1 and this 0. Okay?
Thank
So
you.
now this is PP and this is CNO. Okay? Now, let's be honest here. This is a theorist's way of looking at things. It's not what stars actually do because they don't have to go through the refereeing process. And so they can do whatever they want. And one of the things that they do is these boundaries is not have sharp boundaries. It isn't just that stars don't have walls. It's that fluid motion is messy. I mean, you know this if you have, going back to our discussion from last time, if you have a pot of boiling water and you look at the surface, or better, soup, which is more viscous and thicker, and you don't have to worry just about gas bubbles. When the soup is boiling, the surface is crinkled, and occasionally something will get shot off, and you'll not only be able to hear it, but you'll also see that the structure of the region that's convecting is actually chaotic. Now, what happens at the boundary here, if it's if this were soup, wouldn't make a damn bit of difference, because if a little bit of air gets gulped in because you've got something that comes out and then falls back, it doesn't make a damn bit of difference to the product. The soup will still be the soup. But now think about what's happening here. This is a region which is processing a nuclear fuel. And so if a little bit of this boundary is crinkled or fuzzy, that means that this hydrogen is going to be mixed into the core, and some of the stuff from the core is going to be mixed out. And you would think to yourself, okay, who cares? A little bit of helium gets out, a little bit of hydrogen gets in, it gets a little fuzzy, and big deal. But no, this is a flame, that what you're doing is bringing the fuel in from the outside. This is exactly like what happens in a forest fire. And so you can think of this as the analogy to a, a, the propagation of a flame. That is, what's happening at this boundary is whatever mixing is occurring at the border is bringing fuel into a burning region, which has already, in principle, consumed the helium. Consumed the hydrogen. So this process, this one, the carbon plus P, should, in principle, just cut off. But now you're bringing hydrogen in from outside that can drive this, because the carbon doesn't disappear. It's merely a catalyst in this reaction. This is the important step, that this boundary can make the part that's homogeneous in chemical composition grow, so that over time, instead of the profile looking with a sharp edge here, there may be an extension over time as more of the envelope gets mixed in. This has a term which is unfortunate but necessary to learn: overshoot. There's also undershoot, which just means fuzzy. It means that because you've provoked fluid motion, it doesn't just reach an end and say, stop. Some of it goes a little bit farther, some of it doesn't, and the result is the mass of the core. And in this case, in these stars, the core is directly identifiable because of this boundary in composition. The mass of the core increases over time to the point where, depending on the degree of mixing at the boundary, the core can exceed several percent of the total mass of the star. So what this does is twofold. First, as the burning proceeds, the star is going to necessarily expand. And this is because over time, the bulk of the star is still transporting energy radiatively. And so it's going to have to mechanically respond to that. And because the luminosity of the core isn't constant, and it's also shrinking. And so you have a combination of things that cause the star to move, sorry, cause the conditions of the surface of the star to change systematically so that here the radius increases. Okay? This happens over the lifetime of the nuclear processing in the core until you get to the point where there is no longer a possible continuation of the reactions. In other words, you can't bring more hydrogen into the core. The boundary has finally reached that point where whatever mixing is occurring is ignorable. And at that point, of course, this takes time because you have to you're dealing with a finite core, one that's of order a stellar radius and sorry, a solar radius and size. So it takes time for the conditions to adjust uniformly, but these are short compared with the overall evolution of the star. So what ultimately happens is that although the core is now hot, it's no longer able to continue burning. The next stage in any possible nuclear reaction, remember, this is now helium. So you don't have hydrogen anymore. And to produce anything beyond helium would require deuterium or it would require helium-3. There are a number of isotopes, all of which are light isotopes, but otherwise you can't go from the helium plus carbon to do anything until, because of the Coulomb effect, until the temperature is forced to rise. Now, this is where the fundamental concept of stellar evolution as a mechanical equilibrium comes in. This is something we haven't talked about, but it's really simple. Again, the requirements, if you're going to build a star, are that you have to meet two conditions. Okay, so you have to meet two conditions. One is thermal balance. In other words, energy you're generating in the interior ultimately flows out to space. And the other, if you want to build a star and not just something that's going to blow up in your face, you want it to be mechanically stable. That is, you want it to be physically balanced so that the outward pressure forces are balancing the weight of the upper layers. In other words, mechanical equilibrium or hydrostatic, as we've talked about. Now, if a portion of the star is losing energy, and that energy is, in other words, it was hot, and that energy has to pass through the outer layers of the star, it means that the inner part of the star is in effect losing thermal energy. Its internal pressure and internal pressure gradient is dropping relative to the outer part. Okay? And if you lose pressure support, you begin to contract. So the key for understanding what happens when you've finished any nuclear process is as soon as you don't have an energy source, the only choice you have is to continue losing energy. Okay? You got this hot thing in the core, and the outer layers are necessarily cooler and necessarily more distant and bounded only by space. So you turn off the source, and instead of it just sitting there like a log, that's slowly cooling, it contracts. And this, because of the amount of mass involved, is actually an energy source. Okay? The contraction of the core does work on the envelope. And all of stellar evolution can now be understood as simply that interplay, that what's happening in this stage of expansion is that here, the core, which I said, here it's compositionally different. So the core is contracting and the outer layers are expanding. And this is no big deal. It's simply that the system is thermally and mechanically coupled. So if one part in any way releases energy, it does work on the other part. And releasing energy in this case is gravitational energy. There are lots of ways of talking about this that make it seem almost mystical. One of them is that it's a mirror effect, and so you have the core contract, and somehow this is reflected by what's called the virial theorem in the expansion of the envelope. And don't worry about that. It's simply that this is an integral structure. It's not that the envelope somehow is floating off in space. These are connected. So whatever one does, the other has to reflect. So, in other words, if the outer layers expand, then even if the luminosity is going up, the temperature of the surface is going down. And so the star follows a track on this diagram that moves progressively toward lower temperature. And this is referred to as post-main sequence. Okay? Post-main sequence means, and it's the case for both of these. I'm not going to go into some of the details about the individual pieces because that's only going to be confusing. But what is important is that as the core is contracting, it is, of course, heating up. It's losing energy, but that doesn't matter because it's gravitationally bound. And so at some point in this process, the temperature in this outer region, which is still hydrogen, or still has hydrogen, may go above the threshold for this reaction. And so you go from a star, if we take kind of model of the interior, so this is radius, and we'll say that this is time. So initially, you have the core here burning, okay? And sometime this shuts off, but a shell, that is a region around the core, may start to burn. Now, again, you're familiar with this. This is like having a forest fire where outside the ashes, it gets sufficiently hot that another part of the forest starts to burn because the two of them are connected. So you have, say, the heat from the now dying fire causing a region around it that has not yet started burning to burn. Okay, again, keep this in mind that nuclear reactions are exothermic if they're charged particle reactions. And so these are always going to provoke increases in temperature in regions beyond where the burning has already finished. Anything that can burn will burn if the temperature gets high enough. The only thing that the hydrostatic balance is needed for is ensuring that the temperature gets high enough. Okay, so far? I realize that this time I'm doing things more technically than usual, and I hope it's clear. So let's go to another screen now. So,
So, Steve, the CNO process is for stars that are like high mass and the proton's a low mass.
yes, in the core. But in the later stages, all of the stars will go through CNO. Oh, but in this thin region around the core. In other words, the initial reaction depends on the mass. So the more massive stars, above a couple of solar masses, will primarily generate energy by CNO. Those that are below a couple of solar masses won't reach that physical temperature or density, and instead they'll burn by proton-proton. The thing that you've got to keep in mind is that even if you've got CNO, you still have the PP reaction. It's simply not important. One swamps the other because of this difference between a permitted and a forbidden first step. That in the first step of the proton-proton, there's a weak decay. In the first step of the CNO, it's just a single charge particle. That's the only difference. But in the later stages, when this region around the core that I was talking about gets ignited, that's only CNO. Proton-proton plays no role. It's far too, it's inconsequential relatively for the amount of energy that's going to be released and for the rate at which it's released. Okay? The the thing that happens here in again following the track of the star is that as it so these are lines of constant radius. So as the radius increases and the temperature decreases, the whole structure of the envelope is changing. It's really important to keep in mind that when you see this kind of track being drawn, this isn't what the star is doing. It's not moving on the HR diagram. You've got to think, okay, what does a star with these physical conditions at the surface, this luminosity and this temperature, at this radius, what does it look like inside? These stars are, well, if you start out with a couple of solar masses on the main sequence, this would be like a late B or an early A star. So the surface temperature here is going to be like 10 to the 4. And somewhere here, the temperature might be of order a few thousand degrees. Now, you know what happens if you take a gas like a stellar atmosphere and somehow cool it. That is, you drop its temperature, which really means that you're lowering the kinetic energy of the constituent medium. You go from a medium of ions, like iron 2, neutral helium, titanium 2. So you have metals that are contributing, you have hydrogen that's contributing, but as the temperature drops, it's possible to also form neutral species because the ions recombine. And some of the ions that actually have low enough ionization potentials that they're neutral and become important absorbers. And worse, as you lower the temperature below about 4,000 Kelvin, you hit the point where you get the formation of molecules. Now, remember, The whole point of thermal balance is that the energy that's going into the base of the envelope has to come out of the surface. I keep emphasizing this because once you get this and the mechanical part in your heads, all of stellar evolution suddenly becomes clear. The only thing that's driving the evolution of the star as you see it from the outside is this requirement that you can't store the energy inside the star. It doesn't have a refrigerator where you can put the photons, close the door, and keep them sequestered. I know that sounds silly, but it it's something we're so used to, of the idea that, well, you can make sure you don't lose the energy, put a coat on or something like that. If you do that on a star, it's the equivalent of changing the opacity. And that does bad things. Because if you impede the flow of the energy by radiation, and we talked about this last time, the only alternative is the medium again turns convective. And when it's convective, that sets the temperature structure. So what happens is that as the star moves across the diagram, at this point where it starts to form molecules, the opacity goes up and goes up fast, which means the envelope has to suddenly expand, not because the luminosity of the core has changed, but because the opacity of the envelope has changed, and you go up the giant branch. Convection is a very efficient way of transporting energy. So the surface luminosity goes way up. And the result is that the radius of the star increases as a red giant, hence the red giant branch, which at the same time in the interior is accompanied by the core having reached a higher temperature because it's continuing to contract. What happens in lower mass stars, and by low here I mean below about a solar mass or so, is that the conversion hydrogen to helium by proton-proton in the core and CNO in the shell has led to a core at this point that may be, if it's low enough mass, below about 0.8 or so solar masses, that may be so low temperature that it actually becomes degenerate and can never, if it becomes electron degenerate, in other words, it looks like a white dwarf in the interior of the star. If it reaches that stage, it stops contracting. It may never get sufficiently high temperature that the helium can actually begin processing. So that star is going to eventually produce an inert central core that's going to be a low mass white dwarf, and we'll come back to that. In the intermediate range, around a few solar masses, the contraction may continue to the point where you get helium actually igniting. Now, it's a peculiar reaction. It's that helium 4. In other words, alpha plus alpha plus alpha goes to carbon 12. This may happen. It requires more energy than we needed to get CNO. Well, because now instead of taking, now we're taking two protons, slamming it into 2 protons. It's also a triple reaction. Why it's a triple reaction is because you have to form an intermediate cluster here and then have another helium smash into it. If the temperature is right, this can happen. And you'll get the helium being converted to carbon. So this is referred to as the triple alpha reaction. Again, this is only in the core. It has an incredibly high temperature sensitivity. It's a resonant reaction. But what's important in this is that it has a threshold. And stars that are a couple of solar masses cross that threshold, but at such high densities that you actually get the repeat of what gives rise to the nova explosion. You get a thermonuclear runaway. That is, you have triple alpha producing an enormous amount of energy release, but in a degenerate environment. Meaning the pressure doesn't increase as T increases, but the reaction rate accelerates. So this is essentially a nova in the core of a star. The reason it doesn't explode is because it's got the whole damn star above it. In a nova, when this occurs, it has like 10 to the minus 5 solar masses. So we're talking about 4 or 5 or even 6 orders of magnitude more material on top of the core than you have in a nova. But the physics is the same. The core suddenly convects, the reaction rate goes wild, the temperature keeps rising, the luminosity keeps going up, but mechanically the core doesn't respond by expanding, not at the beginning. It keeps convecting. But eventually the temperature becomes high enough that the core does expand, at which point the star finds itself in a new physical state here. And this is referred to as the horizontal branch. This is core helium burning. That is, this transition.
À 100%.
Sorry? Okay, I hope you realize how this relates to what we've been talking about in terms when we were just discussing novae, because it is exactly the same process. In fact, part of it is even the same reaction sequence. This transition from the red giant tip to the horizontal branch is a dynamical phase. It's extremely hard to calculate this. And so the way that models are usually constructed is you find the analog here, on the horizontal branch to what you found on the main sequence. Let's go back, or let's go to the other slides now, so I
Hey,
can,
Steve,
yeah,
is this the
please.
beginning of the asymptotic
No,
behavior of the star?
we're not there yet.
Okay, I
Don't
thought
worry. Don't worry, we're gonna get there. I promise. Um, okay, this is um, this is Gaia. Um, okay, so here. Okay, so this is the color magnitude diagram, HR diagram of the galaxy. Uh, the main sequence is, well, the main sequence, but you can see that there's also this giant branch. And we'll forget for the moment about the white dwarfs. I just want to concentrate on this part, that in these colors, you can see why this is called a red giant branch. And the only reason that this is so extended in the lower part is because you, in the lower main sequence, have an enormous fraction of the stars of the galaxy relative to the upper part. You also see that there's a very big difference in the number of stars that are on the giant branch and on the main sequence. This has to do with finding stars in those stages, which means that it's related to the evolutionary time. Now, what I meant by the horizontal branch, so just to show one other, this is the double cluster in Perseus, where again, these are field stars, so just ignore them. The red stars are the stars of the cluster. And you see, this is the result of stars, some of which started on the main sequence here, some here, some here. And this is just the snapshot in time of where you find these things on those tracks. So the interpretation of color magnitude diagrams is that whenever you see them, they're the snapshot of the population at one moment in time, but with mixed initial compositions and mixed initial masses. We'll assume if they're a cluster that they start out with the same composition, but they might not if it were a galaxy. So what you've got from the diagram that I was showing before is that the main sequence would go up here, but stars in the time that these stars have gotten to this physical state, stars from a higher mass will have gotten to this state. So, uh, that's um, that's an open cluster, galactic cluster. This is a globular cluster. It's never mind that these are different filters. Uh, these are HST images, so they're ultraviolet and violet filters. The part that's important is that, again, this is color, which is the same thing as a temperature measure, and the magnitude, which is the same as the luminosity. And you see that there's a locus of stars here that's sort of horizontal, even though it's not in these other filters. The horizontal branch got its name from the UBV colors, that if you take B and V and use that to characterize a temperature, and you use V to characterize the luminosity, then stars in this cluster would have a branch here that's kind of horizontal. Great name, huh? So this is the locus of stars that are core helium burning. Those stars are the remnants of whatever happened here when the stars were on the red giant branch. Okay? 47 Tuc is a globular cluster. The stars are old, they're low mass, but all of the stars that have core helium burning are going to be located more or less in this part of the diagram. Okay? Now, if the only thing that happens in core helium burning is the conversion of helium to carbon, then it's exactly the analog of what we were just talking about for the main sequence. In fact, this is called the helium main sequence. or helium core burning sequence. The core is now going to convert over a smaller region because of the temperature dependence of the helium reaction compared to hydrogen. So each time a new cycle, a new nuclear cycle is initiated, it's converting material to heavier constituents, but in a progressively smaller region. So when we were here, so when we were looking at the main sequence, we had here helium, and so this is hydrogen. Now we have hydrogen, helium, and carbon. And again, the carbon, when it's being produced by helium burning, is a region that also is vigorously convective. And so helium is going to be mixed into that zone, and hydrogen is going to be mixed into where you have the helium. And so now, instead of having, as we did on the main sequence, one nuclear source, now we have nested nuclear sources. We've got forest fires around forest fires around forest fires. You could think of this, if it helps, as, say, dry paper with dry leaves around it, and then slightly moister leaves around that. And each one is burning at a different rate, but each one is dependent on the others burning. But they're all simultaneous. So instead of having just one nuclear source, you now have several, each of which, this is important, has a different temperature dependence. Helium burning is much more efficient and much faster than hydrogen burning. Carbon burning is much faster than helium burning. So in this, we're going to have a core, which is, say, triple alpha going to C. Then we're going to have CNO, and then nothing. So this is going to be convective. This is going to be convective. Okay? And there may actually be a gap between them because the temperature has not yet gotten to the point where we can burn the triple alpha. Okay? Then, in a later stage, once we've got carbon in the core, the carbon may be exhausted, but here we have triple alpha, and here we have CNO. And now we've got a different structure. We have two burning zones and the core. And each one of these changes where the stars are. That is, once helium core gets exhausted, the star now moves up like this. And then as it's going up here, it goes into this structure. That's the asymptotic giant branch. That is, it's a double shell source. That,
So, Steve, at this point, is the core inert? The inner core inert?
yes, yes. It hasn't, it has not yet, if it may never.
Get hot enough.
It depends on the mass of the star. It can remain inert. It can stop at several different stages. Now, this is the other thing that's important about CNO versus triple alpha, that you can have triple alpha going to carbon 12. Okay? but then the carbon 12 can go to oxygen 16 if the temperature is high enough, because you can now slam yet another alpha particle in here. If it's really high, this can go to neon 20. And it may even go higher than that. But in general, what you'll have in the lower mass stars that go through helium burning, so the stars that are above, again, the numbers are not critical, above about a solar mass, can go through this. If they're above a few solar masses, they can continue to oxygen and possibly even to neon. But those will be inert. They're not yet going to be able to burn. Okay? When you've reached that stage, you've exhausted the helium supply in the core. And so you've converted it to carbon or oxygen or neon, but what's going on the outside is these other reactions. You're not going to get oxygen production in the shell. It's not going to get that hot. If you're going to get oxygen, it's going to be in the core. So you'll wind up with a core which has a composition of CO or oxygen neon or perhaps even magnesium. But it's enough to say these are the two main possibilities: lower mass, higher mass. If this sounds familiar to some of you, novae come in two varieties: those that are formed on CO white dwarfs and those that are formed on oxygen neon. This is why that if you were to strip the outer layers of the star, what you'd be left with is one of these two. And since they can't burn, they can only cool. And if they can only cool, they can only become degenerate. So ultimately, if the star cannot go to the next stage of nuclear reactions, which is the initiation of carbon burning, this is it. Even if you mix a little bit of helium into the core is going to grow a little bit. It may actually go from CO to one which has some oxygen and neon, but that's it. You're not going to get anything beyond that. So, what happens in this other part? Because you don't know what the hell is going on in the core. The reason being, you've got a whole star between you and the core. So, what you're going to see is the surface conditions that are produced by these different reactions. But one of the things that's important, if not the critical thing, is to go back yet again to thinking about a forest fire. That if you start the burn and you almost completely exhaust the fuel, but you don't quite, if there's a way of starting the fire again, it may pump more oxygen into itself and then exhaust and then get started again. In other words, you can have a fire which reignites multiple times because it never really goes out. Double shell sources are very much like that. The reason is connected with what I was talking about in the temperature dependence, that CNO is not as sensitive to temperature as triple alpha. So if you have a temperature fluctuation, as you will, that's the reason you see the convection in the first place, that the temperature isn't uniform. So little fluctuations are going to drive noise, and that noise is going to be amplified by resonances in the system and by feedback. everything we talked about last time for pulsation, except here it's deep in the star and it's in the intrinsic properties of the nuclear source. If the temperature goes a little bit up, the luminosity goes way up, and the outer envelope expands, the energy is transferred outward, the system now you would think would relax, and then you'd have a pulse that would move out as thermal pulse, and that would be the end of it. But it doesn't work that way because these two zones are coupled to each other. The energy isn't just transferred outward, it's also transferred inward because there's convective motion and turbulence. So these two shells are reacting on different timescales with different sensitivities. And the result is this system is wildly unstable in a way that produces over time a luminosity that does this, where the time between these pulses is of order centuries. These are called thermal pulses. What happens in the high luminosity phase is that the convection zones merge and the whole envelope can turn convective. So let's go to another slide. So this will make it a little easier. So you have so here have convection in these two shells, which now goes to a higher luminosity, and this outer front moves outward. And so this expands, and the whole thing turns convective. In other words, what you've done is a nuclear source. Understand, this is a nuclear source. You've changed the driver. Suddenly goes bright. The envelope goes convective. And material from the nuclear zone is now mixed outward. If this sounds like Chernobyl, it is. The core breaks down and the stuff is dynamically convected outward and pollutes the outer layers. When this zone now goes back to normal, what's happened is core material is now mixed into the outer layers, where here it originally, say, hydrogen and normal. So, okay? But what was the material? I hear you not ask. It's carbon and oxygen. In other words, the stuff that was being produced in these nuclear zones are the light elements. And those have been now mixed into the outer layer. And when the star goes back, when it relaxes back, so after this luminous pulse, when it relaxes back, leaves behind this. So what you will see in this is a change in the composition of the surface. You may not see it in real time because most of us don't go into retirement after 1,000 years, but, and not all pension plans will allow you to stay active for that long. but in a population, they'll show up. And these are stars on the AGB. In other words, double shell sources and thermal pulsing produces a deep mixing by convection of the envelope that reaches into a portion of the star that had undergone nuclear reactions. No other stage of evolution does this. Stars do not mix their guts until they get to the stage where their nuclear source is unstable. And that is in the latest stages. What's even more important here is that it isn't only CNO that gets affected. We also have other very important species. So let me go back to a basic piece of nuclear physics. The first stage of carbon processing of CNO is, sorry, this should be, so yeah, 12C, it's P gamma. This goes to nitrogen 13. Okay, nitrogen 13 decays to carbon 13. Now, normally in the core of the star on the main sequence where this is happening, this C13, which has the same charge as C12, immediately undergoes a P gamma capture and goes to nitrogen 14. And life is good. But it's also possible that this reaction could have the C13 mixed out of the zone if there's another mixing process. This assumes that everything is going to be homogeneous. But remember, I said that these pulses last only decades. So it's possible that the C13 can be brought up into the outer envelope, preferentially. This stuff wasn't there. This was. The 12CO, the 12C was already produced by previous generations. That's the seed. But the 13 is a first product. It's a principal product. So producing this is going to get you here a ratio of C12 to C13 that's different than what we have in solar. Okay? Spectroscopically, you'll see that in the structure of molecular lines. But rather than dwell on that for now, let's continue with this point that this process, this mixing, is given the name dredge up. This happens several times in the life of, yeah, that's miserable. Excuse me. We'll call it excavation by deep convection. It happens in pulses. And the important thing, excuse me, for the production of the C13, the part that's important is that C13, excuse me, is C12 plus a neutron. I hope I'll be forgiven for a moment I need to get something to drink. So, if the C13 is mixed back down into
we lose the signal, Steve. You are mute.
yeah, I muted so that you don't have to hear me dying here. If the
No
C,
problem.
okay, if the C13 is now mixed into a region where the temperature is high enough, the C13 can actually, by combining with a proton, you can knock the N out and go to N13. That is, you can, if, I'm making this hard, if you've produced this isotope of carbon, it's got an extra neutron. Neutrons are not tightly bound, but they can be kicked out by a substitution just because there is going to be, if you can get the first reaction going, if you can get C12 P gamma going to N13, then you can also do C13 plus P, okay? Knocking the N out and substituting for a carbon, which means now you have nitrogen 13. Okay? So far?
Steve, just a minute. I think we have lost your video. Can you check, please?
Um, okay?
I see his
I
mouse
see it,
moving.
Francois. I see it.
You can see the whiteboard?
Yeah.
Yes, I can.
No,
Okay,
we
in
see
other words,
the whiteboard.
yeah, that's all. Okay, so
Instead of video, your image.
I'm deliberately keeping the video off for the moment.
Yeah, I have to too. My internet's too
problem.
unstable.
Okay,
Sorry.
so as long as you can hear me, the part that I'm trying to emphasize is that now you suddenly have a new source appearing in the interior of the star that is not releasing energy but does something really remarkable. You suddenly have a neutron source. You've built a nuclear reactor here. You know, the one of the things that you use nuclear reactors for is to get a neutron chain reaction going, which produces a high neutron background. So one of the reasons these were used in, say, the 50s and 60s for medical purposes was you wanted to get a high neutron background. Well, here it is, that the same thing that's producing the CNO process that was giving you the carbon 13 here by decay of the nitrogen 13, lo and behold, we can go the other way around. So you produce the C13, you mix it back into the region where it can now capture a proton, except now you don't liberate just energy, you liberate a neutron. That neutron is now available to be captured because it's thermal by anything that's in the core. That's the important thing to keep in mind. This gets to the most important step in stellar evolution. Although you can say that the formation of C, N, and O is kind of important because that's what we're made of, and phosphorus and fluorine and everything up through the Iron Peak. The thing that really is important, if you believe that AI is our future, is rare earths. You can't build the heaviest elements in the universe, anything above the Iron Peak, by direct charge particle reactions. They're not stable. But neutrons do not have an electrostatic potential barrier. they can be absorbed by any nucleus. And so you can get the capture of a neutron by carbon. You can get a capture of a neutron by iron. You can get capture of a neutron by calcium. What happens in that capture is what is so important in determining what the element will do. That is, let's say you have a charge, number of protons zeta, and a nucleus with an atomic mass A. So this is the charge. Okay, it's the way that I've been doing, the way I've been describing things here. So if you have a capture of a proton, this would go to zeta plus 1 and A plus 1. Okay, in other words, you would go from, say, carbon plus a proton going to nitrogen 13. Okay? So carbon 12 plus a proton going to carbon 13 to nitrogen 13. Nitrogen 13 is unstable, so it decays. But you could also have this capturing a neutron, emitting a gamma, and now going to zeta A plus 1. In other words, you have a heavy isotope. And another neutron would give you A plus 2 and A plus 3. And you're still not changing the nuclear charge. So in other words, this is endothermic. You're using energy to insert the nucleus, to insert the neutron. But eventually, because of a nuclear structure, the nucleus will become unstable and it'll decay. It'll go through a beta decay and go to zeta plus 1, A plus whatever. Okay? That's the chain reaction that gets set off by this. If you can knock neutrons out of the carbon 13, which doesn't require that you actually produce gammas here. This is a particle that's being lost. So you're not going through full nucleosynthesis. All you're doing is liberating a thermalized neutron, and that neutron can now be absorbed. And you see by this decay sequence, it produces a new element. This is what Joliot-Curie and Fermi and the work of the 1930s produced with the idea of having slow neutron capture leading to nucleosynthesis of light elements. So what's happening, we can see from going to, okay, preview here. So what you wind up doing is, okay, this is the nuclear chart. I had planned on showing this later, but I'll do it now. The black, so for those who aren't familiar with this, the atomic number, that is the element, goes this way and the atomic mass goes this way. So for each element, these are progressively more neutron rich. The stable nuclei, that is the ones that we know have effectively infinite lifetimes, are shown in black. All of the others are either detected in the laboratory or theoretically predicted All of them are the available isotopes of these. So for example, you see that for neon, there are 3 stable isotopes. For carbon, there are 2. For nitrogen, there are 2. For oxygen, there are 3. Okay? Just because of the peculiarities of atomic structure. So if you can build C13 and then knock out the proton, that proton is, sorry, and knock out the neutron, that neutron is now available to be absorbed by any of these, which will lead to the formation eventually of a species that's unstable. So let's imagine that you capture on nitrogen. Okay, so C13 produces a neutron. That gets captured on N14. Okay, let's say N14 goes to N15. But N15 is unstable, and so it decays here. Okay, so far? That is, N14 goes to N15, which goes to N16, which decays to oxygen 16, which may then itself absorb a neutron, absorb another neutron, absorb another neutron, and become unstable, and now decay to fluorine. You see what's happening is that if you've got a few of these sitting around, if you've got a few of these seeds and the neutrons are actually going to drive nucleosynthesis. But it's a slow process because it depends on the charged particle reactions, the ones that are producing the neutron background. Hence, this is referred to as the S process. S for slow. The elements that are further up the table, so now above argon and above calcium, in other words, here, iron, nickel. Now, if these capture, they may go through a sequence building all the way up to heavy elements. You could start with just iron, expose it progressively to more and more neutrons, and what you're going to get is this sequence of building up heavier and heavier elements. And if you continue that, it's going to go even farther. I hope you can see this one. Now we get into the rare earths, which is why I made the crack about AI. That is, we can start out with iron and we can end up with elements like samarium, gadolinium, neodymium, cerium, lanthanum. In other words, all of these extremely neutron-rich, heavy elements started with simple neutron exposure on the elements around iron. This is going to happen because in the process of that dredging, you've mixed the elements, you've mixed the isotopes that become the neutron sources into the regions that have temperatures high enough to liberate the neutrons. This is the other key point about the AGB. It produces peculiar elemental compositions, and you see those in the atmospheres of the stars themselves. The other thing you see is, well, in fact, here. Excuse me? Was there a comment?
No.
Okay. Um, so this is an example. Can you see the screen now? This should be showing the structure of uh, the interior as a function of time.
Yes.
Yes, we did.
Okay, this is from a moderately massive star. It's about a 6 solar mass AGB star. But this is a calculation by Elid from, about 10 years ago that just shows what happens during these thermal pulses. This is one of those pulses where, as I mentioned, you get this deep convective layer that actually gets mixed into the outer part of the star. The way you can read this is the structure is the vertical line here at any moment. And so,
Hey, hey, Steve, what's the
yes,
x-axis for
time,
clarity? Time. Oh, thank you.
okay? It's time in years. So when I said that these are very rapid and they take centuries, they really only last for centuries. That what you're seeing is real-time changes in the star where this stuff gets mixed. There can be many of these. The time scale between the individual events is a mere couple of centuries in the later stages. And in each case, you're mixing these neutron producers into regions of the envelope that have high enough temperatures that the neutrons are being liberated. So the structure of the star, well, the structure of the star actually looks something like this. These are 3D models. We're now at the stage where several groups have been able to effectively model at least the large scale structure of the convection in the outer layers of these supergiants. The interior looks sort of like this. This this is a calculation that ran for the equivalent of a day to get to this stage. And I don't mean a day of computer time. I mean that it simulates, we're at the point now where we can simulate a few days of stellar evolution in 3 dimensions. But it's enough to get a rough idea of what things look like in the interior. So this is actually what you would expect for the distribution of a neon, uh, one of the neon isotopes, a neon 20, in the interior of a giant after a few days of it deeply convectively mixing. Uh, this is still a very, very thin layer, but
And Steve, the red is carbon and the dark blue is oxygen.
the dark blue is the neon.
Oh, dark. Okay,
So,
thank
in other words, what you're getting mixed in here is material that's been processed, and here it's just thoroughly mixed. This is the same sort of thing that we see in the initiating stages of novae. The difference is in a nova, this stuff takes a matter of tens to hundreds of minutes, and here it takes tens to hundreds of years over the whole cycle of the star. But again, everything that we've been talking about in earlier discussions is showing up here. That on the left-hand side, it shows again with time the way that the mixing is occurring in 3 dimensions between between carbon, neon, and oxygen in different models. This is a comparison between different ways of doing the calculation, but the thing that's important is you actually are getting thorough mixing because these are very turbulent. The structure of the interior looks something like this, that when it's going through a thermal pulse, these are circulation patterns that at the moment are available for calculations where you get a very deep mixing in the envelope between these different shells that are burning at different rates. And then you also have circulation in the atmosphere that's set up because of atmospheric waves and other perturbations and pulsations that we were talking about. So going back to here, as these pulses continue, the composition of the surface is going to change. And one example of how this actually happened was this star. I remember as a child first reading about this, that it was this, this is the AAVSO light curve for FG Sagitti, beginning in 1970 and showing that over the life of this star, it went through some phases of very, very different large amplitude fluctuations. But the thing that's most important in this star, I think, is this paper from 1968, in which Herbig and Biarchuk pointed out that this was a star that had changed its spectrum over a mere 5 or so years. That, as they say, Coude spectrograms are available from the years 1960 to 67, information from low dispersion from 1955. Over that period, the spectral type changed from a B4 supergiant to an A5 hypergiant. Now that's pretty remarkable, but it also turned out that the composition changed. The star started to show barium. It started to show heavy elements, not just because the temperature had dropped, but actually because the composition appeared to be changing. The high luminosity is interpreted as due to gas lying above a false photosphere, which itself is rising very slowly in the rapidly outflowing material. All of that is the interpretation of an epoch. The thing that's important is FG Sagitti was one of the first stars to show this compositional change. There are other stars that have shown, in addition to changes in the heavy elements, changes in the light elements, specifically one, lithium. Again, we come back to the technologically important species that the, okay, wait, come here. So if we have helium-3, which is a stable isotope, and the temperature is high enough that we can have helium-3 plus helium-4, then this can go to beryllium-7, which decays to lithium-7. Why you care about this isn't just because you can build batteries, but lithium is produced in only two places, either in the Big Bang as a product of a reaction like this, but very short-lived, or in stellar interiors, but it's generally consumed because lithium has a very low threshold for proton capture. On the other hand, it was found that in red supergiants, the lithium line can be very strong. Now, you know, I think I hope from our discussion of pre-main sequence stars, that lithium is taken as an indication that a star is very young, because if you see lithium on the surface, it generally means that it hasn't yet been mixed into the interior the way you would expect in a star like the Sun, and so it hasn't yet been consumed. Lithium, like deuterium, gets destroyed at very low temperatures by proton capture. But there's the other way around, that lithium, if it's if it's produced in the interior, if it can be mixed outward before it undergoes destructive reaction, it'll show up at the surface. So an indication of deep mixing in these advanced stages is that stars can show very strong lithium lines and yet be very old instead of very young. These are, there are a number of them, uh, W zeta Cas and WX Cas being two very good examples. But even some symbiotics show it, that they are so evolved and they've gone through this kind of thermal pulsing and this deep nuclear burning with mixing that they show this pollution by lithium at their surfaces. Now, there's another thing that gives us a clue to all of this, and that's this: chondrites, meteorites. This is the only time that I'll be able to give you an example of something that you can literally hold in your hand that's directly connected with a star. We normally think of meteorites as relics of either asteroids or the formation of the solar system, and tend to forget that if something has fallen on your head from space, uh, it had to come from somewhere originally. That the gas that you have condensed into that meteorite was from the interstellar medium. And one of the things realized in the 1970s was that embedded within the carbonaceous chondrites, these chondrules are small structures that are sometimes as contains smaller grains that are as small as tens of microns across. Some of the most primitive material that has not been shock processed, namely these kinds of chondrules, can show some very peculiar abundance patterns when you put them through a detailed mass analysis. They show carbon and oxygen and nitrogen isotopes that aren't solar. So these are the solar value, that is 17 to 16 and 18 to 16, is marked here by the intersection of these two lines. So where my arrow is, that's the solar value. Individual chondrules and individual grains can depart from that, which means that the material that condensed had a different isotopic composition than we see in the sun. Okay? When you analyze them carefully, this is what comes out. That using nitrogen isotopes and carbon isotopes, the solar value is here, and there are distinct groups that have different isotopic ratios, and those match what you would expect from this neutron processing. In other words, some of these grains contain the chemical signatures of having been born and processed in the envelopes of evolved stars and then expelled and incorporated into the gas and dust of the interstellar medium from which the solar system was formed, but that retained their identity because of just random chance. They were not destroyed in the process of condensing the material that became the asteroid or the meteorite or the planetesimal. And they've survived intact without changing their compositions. These are called pre-solar grains. There's a whole subfield studying these. But the thing that's important is that here you have different groups of meteorites that show different chemical compositions and that contain, to show again here, contain single nodules that predate the solar system. They are not grains that were formed in the solar nebula from the mean composition. They're grains that were formed in a different environment and weren't evaporated in the process of forming the meteorite. That indicates that the material that these stars produce, the AGB stars, is not only mixed into their envelopes, but it's expelled. And that gets us to the last part, which is to remember that when you increase the luminosity, if you increase the radius and you decrease the surface gravity, you've got a perfect way of driving material off a star. You can get a stellar wind. The AGB stars are the highest luminosity for their mass. They are the end state of an evolution that has produced progressively higher luminosities in progressively more distended objects, and with surface temperatures that are low enough that you're getting not only molecules, but you may even, in those environments, that's what this is telling you, form grains. That these pre-solar grains are the demonstration that the material that's lost from AGB stars has been able to condense in the environment in which these compositions were present. Okay? This is the same thing as forming soot in the laboratory. If you put soot in a high radiation field, you're going to be able to drive by radiation pressure, by a radiative acceleration, that material off of the star. So the one thing that we know from putting all of this together is the AGB nucleosynthesis signature says this material that we see in the pre-solar grains condensed in the environment of the star, not in the circumstellar environment, in the envelope of the star itself. It was then lost by the star. It doesn't matter whether it was by pulsation, by radiation pressure, or both. It was lost in sufficient quantity that it was able to make it in so bloody dilute a medium as the interstellar medium from the nearest AGB stars to us. Okay? Now, think about this. This is the same thing as looking up tonight, wherever you are, at Orion, and looking at Betelgeuse and thinking to yourself, you're polluting me, because that is an AGB star, and that's producing dust, and that dust is being lost, and it has a strong wind, and it occasionally even puffs out obscuring clouds, as it did a few years ago. That and stars like it are half a kiloparsec away. So these are grains that have managed to make it into the solar nebula in sufficient numbers that we can find them, which gives you an idea of just how much mass is actually going to be lost by an AGB star over its lifetime. You're talking about stripping off the outer layers of the star. If you do that, you get two things. One of them you're very familiar with now. You get a stripped core, otherwise known as a white dwarf. Well, it's first called a post-AGB star, and then eventually it becomes a white dwarf. The other is a planetary nebula. That is, as you strip the material because of the formation of these molecules and because of the extended wind that it's driving, and the pulsation that results. That was the example I was showing you with FG Sagitti. If the star is now surrounded by all of this junk, but it's dilute because it's now in a wind, the core is going to ionize and illuminate it. And so in the end, you wind up with a planetary nebula. Now, what we don't know is the fraction of stars that become planetaries, so here, that are binaries. This happens to be a planetary that was formed by a merger. But if you have a star like Betelgeuse, the radius of this thing is enormous. So if you have a companion that has a period of only a couple of years, it's potentially going to be inside the envelope of that star. And so we get back to our discussion of mergers, that one of the things that can also be important in the AGB and the post-AGB, which is not included in anything that I've talked about, is that there may be binaries. In fact, there will be binaries. It's not a matter of may, depending on the distance that the companion was on the main sequence, when the two stars were on the main sequence, it may find itself at any of the stages I've just talked about inside the other star's envelope, or limiting the structure of that star because of the Roche lobe. So everything that I've been talking about up to now has all been for single stars. You've got to keep in mind that virtually every star has a companion of some kind, either planets or a companion star. And the distance that that companion is from the center of the more massive star is what determines all of its subsequent evolution. So you can also see everything that I've talked about being exaggerated, potentially even more mixed and more dramatic in its mass loss and in any of the other consequences if it happens to be in a binary system. It's still the legacy of the 20th century that virtually all of stellar evolution discussions are framed in the context of single star evolution. And after all of this that I've just gone through, I want to emphasize that much of what I've said is only the tip of the iceberg and potentially even misleading if you take it as the paradigm for the way that stars evolve. Single stars have no real boundaries. They can expand as far as they need to. They can develop winds simply because they've expanded so far that the surface gravity has dropped and they just freely lose mass. So what I've talked about in generating winds, in getting the material out, having the nucleosynthesis going, having the envelope structure adjust in order to carry a certain amount of energy, is all based on the idea that you have this free surface that can expand as far as it needs to or contract as far as it must. If you've got a companion, that's no longer true. There is an outer boundary that material can become gravitationally unbound long before it has extended as far as we might need to get the AGB. Everything that I've been talking about and the whole interpretation of the HR diagram is based on the idea that the radius exactly corresponds to the internal conditions of the star and that star alone. If you have a companion, all bets are off because you don't know where you're going to put the little bugger. The companion may be at a period of a year, a period of a day, or a period of a century. Just depends on the initial conditions. The mass ratio may be unity or it may be very large. It doesn't matter. It's something that we don't understand in a very basic way because we don't know what determines that. We also don't know what determines the initial orbits. The third point is that once you put in that companion and you change the boundary conditions because you either limit the surface or you spin up the star because of tidal coupling, or both, you change the mixing and you change the nucleosynthesis. So all of this is the next step in understanding what's going on here. We do, I think we do understand how single stars evolve. Whether that's completely relevant to the picture is the question for this century. The example is the one I'm showing you. This happens to be a planetary nebula that was formed, it appears, from a merger. That it's actually a double cone structure. You can just barely see it. That there's one cone on this side and the cone on the other side that are both in emission, where this is actually like a double ring nebula. And this is the plane of the merger, showing also the dust and the scattering from the dust. So while the while stellar evolution is really very straightforward, if we're dealing with single stars, because we do understand how to deal with spherical stars, even if they're strongly stratified. They're basically one-dimensional structures if they're spherical. But the next stage, the frontier, is going to be understanding what happens when we have binary and multiple systems. And the last part is just to mention that what also I think drives this is understanding that when we look at globular clusters, we see that there are multiple populations in these things, that there appear to be several different stages of star formation, and this has always been a problem we didn't think we were going to have to face. The globular clusters, the oldest star clusters, have always been presented as single generation. You form this blob, it fragments into stars, they all have the same composition. It became the paradigm for understanding everything I've talked about in advanced stages, from the horizontal branch and the giant branch through the AGB. But what we now know is that when you look carefully at high resolution spectroscopy, photometry of the cores and periphery of the globular clusters, you see that it wasn't star formation in a single burst. You see that there are different stages of star formation and they have different compositions, which means that everything I've been talking about, the pollution of the medium, appears to have actually taken place in several stages while stars were forming. So one generation of massive stars goes through these advanced stages, blows material not out of the cluster, but off of the stars, and that gets incorporated into material that has not yet formed stars, but stays bound within the cluster. The role of binaries in that has not at all been addressed. The role of mergers hasn't been addressed. And so everything that we've been talking about is really just the beginning. This is sort of the culmination of everything that we've done from the beginning of our discussions. The pulsation and the driving of pulsation by convection, you see here, becomes much more dramatic, much more violent, and much more distinctly nonlinear when you get to these very high luminosity advanced stages. The process of nuclear burning that you get in novae is the same thing that you get in advanced stages of evolution. The difference is that in novae, it's explosive because there's nothing to hold it back, but it's the same process. The role of mergers, binary stars, symbiotes,